Not long ago, I caved and bought myself one of these pieces of junk. The adult in me knew better, but the kid in me really craved some ultrasonics. When no one was looking, I'd sneak out here in the garage and have some fun with this thing. Now, it's important to me that you understand something. It gets lonely out here. The nights are long. The cold, gray embrace of winter waits just outside that metal door. Things got complicated. Don't judge me. So I got a big one and a small one. I got this one for the express reason of experimenting with it. Despite knowing better, there's something I always wanted to try. This little fella, unfortunately, is destined to live a short and empty life. I'd like to take a shot at turning it into an ultrasonic knife, rather using its guts potentially to drive an ultrasonic knife. Oh, and I'll likely use the terms knife and cutter interchangeably in this video. I don't personally know what the technical difference is, if there is one, so my apologies in advance. Now, I know this might be a little out of character, but it'd probably be smart to try this thing out and make sure it works, lest I end up with a broken heart due to a whimsical yet tragic misunderstanding. An ultrasonic knife or cutter, for those who might have never used one, is basically like one of those electric knives you see on those great infomercials, carving turkeys and cutting cans in half. Like a reciprocating saw moving back and forth very rapidly. In fact, they're ultrasonic. Not supersonic, not megasonic, ultrasonic. This is just a small piece of aluminum foil. It's a cheap dollar store type, about 2 aluminum atoms thick. Not that fancy Food Network ballistics grade stuff you need a pan brake to wrap a sandwich. I want to just get all the air out from behind that. The other bonus to using foil is that it gets as much shiny metal in the shot as possible to make filming this fun-tastic. If all goes well, the ultrasonic cutter might end up looking something like this X-Acto knife. In fact, I'm thinking of using an X-Acto blade as a replaceable tip, maybe smaller. But now, instead of cutting just because it's sharp, imagine this little blade moving so little and so fast that the energy discharge at the cutting edge effectively makes it an ultra-sharp knife, even if the edge isn't necessarily, say, mechanically sharp. In other words, if you tried to cut with an ultrasonic knife while it's turned off, it'd feel like a dull X-Acto blade. Wouldn't cut any different. In fact, it might even cut worse. But if you could drive ultrasonic energy to that cutting edge, then it becomes a formidable weapon. Like a little jackhammer, but a jackhammer you'd find in the tool shed at the Hall of Justice. I want to just get all the air out from behind that. So that's just tap water in there. I'm not going to bother with the heating. This is the heater controls. These are the ultrasonic controls, the timer. I'll just leave it at 5 minutes. We'll see what happens to the aluminum foil. Ultrasonic knives, if you haven't already gathered from their badass name, cut through almost anything like nobody's business. Well, if you have the power behind them, that is. Plastic, food, fabric, you name it. And they do that without any of the crushing forces you'd expect from a regular knife or scissors. But you know what? Instead of me trying to paint you a picture here, and since I can't just steal other people's footage, go ahead and click in this little red circle to pause this video. Go watch some ultrasonic cutting in action, and when you have a good idea of what they do, come back here and click in the little green circle to start again. Here goes nothing. Okay, was not expecting that, but I'll take it. I stopped the timer right at 2 minutes. I think you can probably read that. Started at 5, it's now at 3. So the thing works. As expected, it appears the most power is right above where the transducer lives, which would be right there in the middle. Shall we continue? Before we break into this, let's quickly talk about how ultrasonic cleaners work and what we're likely to find inside. Being the super sleuth that I am, and just going by the name mind you, I expect to find an ultrasonic transducer right about here in the middle, under and attached to the tank. Now I know what you're thinking. Big deal this old Tony. We've now got a tank full of soapy water and sound waves. What's in it for me? The transducer generates and pushes sound waves into the tank, into the water. In this case at 40 kilohertz according to the label. Since that's higher than 20 kilohertz, the upper limit of human hearing, people in fancy lab coats have come to lovingly call it ultrasonic. Ultrasonic waves are no different than regular sound waves, they're just faster. Think of the transducer as simply a feisty little speaker attached to the bottom of the tank pumping fresh beats into the water. They're called transducers because they're real deuces at transing. Sound waves are mechanical. They're pressure waves, in contrast to, say, light or radio waves, which are electromagnetic. Being a mechanical pressure wave, they push and pull on the medium they're traveling through, in this case, water. I strongly feel that this warrants some interpretive dance. In the traveling sound wave, there are sections of compression and sections of expansion. Now, if they do that hard enough, if the pressure is high enough, when the waves pull apart, the pressure can drop so much that it causes the water to cavitate. The fluid sort of tears itself apart, for lack of a better description, creating a bubble. When the pressure comes back up again, the bubble collapses. When that happens, when one of those little bubbles collapse, you get a very, very high spike in temperature and pressure. It's extremely brief, but high temperature and high pressure right where that bubble was. Now, I don't know offhand what temperature that reaches, but it's customary in these situations to say hotter than the surface of the sun. In general, people do everything they possibly can to avoid cavitation, to avoid formation of those little vapor bubbles. If you haven't seen it, Grady over at Practical Engineering has some fun videos about cavitation. When I'm not making videos, you should definitely go over and check them out. When I am making videos, drop them like he's hot. But in the case of an ultrasonic cleaner, we're harnessing the destructive and indiscriminate power of cavitation for the ultimate good, cleaning. While we're here, maybe just a quick FAWU. Formation of those bubbles happens at nucleation sites. I know that's a scary word, very Chernobyl. But it basically means a bubble can't just form anywhere in the vast expanse that is this water tank. There needs to be a small defect somewhere, microscopic, but something sharpish like a scratch or a protrusion, some small particle, some little seed site that can instigate the formation of those bubbles. Now, if, like me, you've spent hours transfixed on the bottom of a pot of boiling water, you'll have noticed the bubbles don't usually just come out of nowhere. They form around these nucleation sites, something to get the party started, as it were. And in fact, with new pots, something that's sort of super smooth or coated in something weird, the lack of nucleation sites can even be a little dangerous. Without boiling, the water can become superheated. Then, as soon as you drop your spaghetti in there, the hot water can blow right out of the pot and burn your face off. Which, let's be honest, is a little bit your fault for adding spaghetti to water that obviously hadn't come to a boil yet. In an ultrasonic cleaner, the parts you put in provide more than enough to get the cavitation going. Well, I'll be. That's actually a pretty decent looking circuit board. I'm certainly no expert, but first impression, that looks pretty sharp. There's the transducer in there, also a lot bigger than I was expecting. Smooth. Not 100% sure how to get that out. So in a cleaner, the cavitation is what's doing all the work, what does all the cleaning. The little bubbles are like a blitzkrieg, cleaning in the little nooks and crannies you probably couldn't reach with a brush. You know those little dancing, scrubbing bubbles that parade around in the bathtub on those detergent commercials? Think of cavitation like those, but angrier and suicidal. The ultrasonic energy, of course, is what drives that. In practice, I'm finding these particular units to be rather disappointing. I mean, they're doing their thing, but with a dirty part in there, it's way less dramatic than what we saw with the aluminum foil. Now, I might not have the right detergent or letting the water get hot enough, I don't know, I'm still learning. But it seems to do a great job cleaning something that wouldn't have been that hard to clean in the first place. Like if the dirt, grease, grime, or rust is the kind that doesn't put up a fight, this cleans it great. Gets in all the little tidbits you might not be able to reach otherwise. That's what it's really good for. But if it's a real rust or oxidation, like a 50-year-old part you're trying to bring back to life, well, you could let this thing rattle along all day until the sound melts your brain out your ears. The parts aren't coming out clean. In fact, not only will they still be just as dirty as before, but now they'll be wet too. There's the heating pad, and up at the top here there was a little temperature sensor. The transducer is 40 kilohertz and 60 watts. It appears to be epoxied to the bottom of the tank. That's not going to be fun to separate. Though you know what I bet might work nice? An ultrasonic cut. Now we're here, the transducer is used to generate the pressure waves in the fluid in the tank, in the water, to induce that cavitation. In an ultrasonic cutter, the transducer would be used to accelerate the cutting edge, vibrating it like crazy. In that case, the energy goes into heat, or friction. It sort of mechanically destroys whatever is in its way. So I'm jumping the gun a bit here, but since we have this in front of us, let's just talk about some of these parts that we're looking at. These terms are going to come up as we're trying to build this cutter. The sandwich that you see here in the middle in black with the two leads going to it is the piezoelectric element. You give it some juice and it goes all hyperactive, bouncing around 40,000 times per second. On the bottom, where the sticker is, would be the ultrasonic horn. This is what shapes and forms the energy coming out of that transducer. This bit is going to get hairy because, frankly, I don't know a thing about that kind of stuff. Behind it, the chunk on top in this view, is a counterweight. So this whole thing, the piezoelectric element, the counterweight, the horn, and the tank, make up their own little dynamic system. See, the tank was mounted to the chassis of the cleaner via some silicone. It wasn't rigidly attached. So this whole mess here that you see on its own, I assume has been designed to deliver the maximum amount of energy into the liquid in this tank. Let me shoot you straight here. What I'm about to try is likely quite futile. I know enough about ultrasonics to know that I have no idea what I'm doing. This is some complicated stuff. We said this whole thing was tuned to maximize the energy in the tank. I don't know enough about retuning that to turn this into an ultrasonic cutter. But for the $60 or $70 that this thing costs, I'm willing to give it a shot. Perhaps someone that does this for a living, or knows more about this than I do, might see me do something stupid, chime in. We give it another shot down the road, and maybe we get to a workable, albeit small, ultrasonic cutter for the shop. As of this video, and only having done some admittedly shoddy research, there appear to be two options if you want to buy one, commercially, an ultrasonic cutter. Either you spend about $400 for a hobby cutter, or you drop $1,000, $2,000, $3,000 for a professional one. Now, I couldn't find hard specs in my 3 seconds of looking, but it appears that the hobby ones push about 100 watts, and the professional ones about 1,000 watts. That's an order of magnitude difference in power, and 2 orders of magnitude difference in how much a hobby one probably sucks. This transducer is 60 watts, which in real life probably means 20. So it's an uphill battle right out of the gate. Just the fact that there don't appear to be ultrasonic cutters in the $60 to $70 range listed as, say, 60 watts, practically speaking, is probably already a big red light. But come on, what kind of YouTube channel would I be running here if I didn't try something stupid every now and again? Let's try to get this little powerhouse off of here. I've got the whole contraption clamped to the bench. Now, I didn't initially want to break this stack, but I don't think I have much of an option here. I'm going to have to make a new horn anyway, so it's not like I really needed that part. Here goes nothing. This could very well be the end of this video. Time for a bigger wrench. I'm guessing this thing is probably Loctited in place. That thing just shocked me. Piezoelectrics, am I right? No Loctite. Okay, fortunately nothing broke. At least I don't think it did. Here are what the parts look like. The mass on the back doubles as a threaded nut that keeps the stack together via that stubby chunk of threaded rod. And there's the piezoelectric stack. It's a sandwich. We've got 2 slices here. The signal or positive goes to the center, and it's grounded on both sides by the spade connector and the conductive path through the threaded rod. A small plastic bushing chaperones those connections so they don't get too intimate. Earlier I referred to the slug on the bottom of this thing as a horn. Probably got a few eye rolls there. It might not technically be a horn in this configuration, but it's the part that will become the horn as we perform the transition surgery. As it is, maybe it's just an additional mass to balance the load on that piezo on the board. Again, I assume someone put more thought into this cleaner than I'm putting in the cutter, but think of this as maybe like tuning the suspension in a car. The piezo and the board are expecting a certain mass, itself plus the tank and the water inside. That's probably why you're not supposed to run these dry. Too light and the driver board goes crazy, like a bouncy car. Flip side, if it's too heavy, like you put your entire bench vise in the cleaner, you'll likely bottom out the suspension and things won't work correctly. Probably a high risk of burning up the board if you run this unloaded. Now the plan is to build this stack back up, but on the back side of a horn that might also take a small blade. The horn is needed to tune and amplify the ultrasound, just like the horn on a, like on a megaphone. A megaphone's got a speaker in it, but without the horn it wouldn't be very loud. And just how a horn needs to be matched to the speaker and frequencies in a megaphone, or an air raid siren, or your boom box, we have to do the same thing here. Now, everywhere I've worked that's used ultrasonics for welding or testing or cutting, don't think we ever did any cutting. I think the horns were always titanium. Maybe stainless, but titanium jumps to mind. And we always had them made by specialists that knew what they were doing, despite having in-house machining departments. Now, I don't have any titanium, or stainless for that matter. So I'm going to dig around and see if I can find something of suitable diameter, of suitable material, that won't make this horn a mile long. I don't know, ideally maybe 4 inches if I can get away with it, 100 millimeters. Let me do some digging and some thinking, and I'll be back in 2 shakes of a lamb's. Alright, well it turns out I did a lot of digging and not much thinking. From what I've learned in the last couple of hours, evidently, one does not simply walk into make a horn. I really should learn to do my homework ahead of time instead of making videos about putting my foot in my mouth. The official way to do this appears to entail making a theoretical horn to theoretical dimensions. Then it requires testing and tuning. It's iterative. You build it, you try it, you modify it until it works. Problem is I don't have the equipment to really do that. With that, and after careful consideration, I've decided to just give up. Thanks for watching. Let's make a theoretical horn and just see what it does, shall we? I mean, I've got a lathe, a mill, and this piece of aluminum. Another hour out here in the garage. Let's do something stupid. Well, here it is. I've already gone ahead and bonded the blade in. I opted to use some epoxy just because the screw was causing some problems. I say the screw, but that's probably news to you folks. I had planned to use a little counterbore torque screw just so I could replace the blade, but it was screwing with the math, or my math. We'll see that in a minute. I figured since this is a test, I just went ahead and took the easy way out and threw some epoxy in there. The blade is bottomed out against the slot in the horn there. Hopefully it doesn't break itself free. It is smaller than I was expecting. Now before I build this back up, before I test... Let's just talk a little bit about the end game as far as the horn is concerned. Talk about how this design came about. The vibration of the piezo, how much it moves when it gets excited, just on its own is very low. Somewhere maybe around the 10 micron mark. Maybe 8, 9, 10. That's about 4 10,000ths of an inch. If you weren't sure, that's not a lot. The horn hopefully serves to amplify that, magnifies it. Just like the horn on the megaphone, remember? A little bit of motion here, whole lot of motion here. Properly built, it should resonate at the driving frequency, at 40 kilohertz in this case because I have a 40 kilohertz transducer. Hopefully that's also why this thing is so short. I say it looks short to me because I'm used to seeing longer horns, but maybe they were driven at a different frequency, like 20 kilohertz or something. I think the lower frequencies have more power or bigger components, so you could do more useful work with them. Now, resonance is a big word. It's hard to know for sure, but it's got to be at least 10 letters. Simply put, it's sort of the natural preference for something to vibrate or oscillate at a specific frequency. Think like a tuning fork or a bell. You strike a bell and it wants to ring sort of at its quote-unquote native frequency, its natural frequency. It has a preference. I guess the classic example is pushing someone off of a swing, on a swing. And ever since I was a kid, and I still get that mixed up to this day. You know that feeling of pushing someone just at the right speed that matches what the swing sort of wants to be pushed at? Just the right push at just the right time and the swing goes higher and higher. Push it out of step with what the swing wants and things go haywire. Kids start to bleed, parents start getting angry. The swing might stop or might require much more energy to push, both of which are the last things anyone wants. And that's what we're doing here, or what we're trying to do anyway. We want to build the swing at the rate that this little thing is pushing it. So we get a little push in the back and a big swing at the front. So I started with some very basic calculations. I know the speed of sound in aluminum because I Googled it. And I know the transducer frequency, or at least I think I know. I'm guessing. The transducer could be running at 38 or 41. The mechanical properties of the aluminum can change so much that the speed of sound changes, depending on the alloy or the grade. Both of those could be so vastly different than what I've got that this might all be a moot point, but theoretical, remember? Those numbers tell me the length of one wave in aluminum at this frequency. I started with a half wavelength stepped horn, with a shoulder right in the middle at the quarter wavelength mark. So far so good, right? However, I don't have just a horn. I have a knife attached to the end. And this is where things got a little extra crazy. Although there are rough guidelines for very simple horns, I couldn't find any specific build details for real horns. Like what would happen to it when I add that blade to the end, or a tool of some kind. So I did what any respectable kid scientist would do in the face of such uncertainty and blindly put my faith in computers. Now here you're looking at the finished horn, obviously, the one I made, but I iterated a lot to get here. Though, surprisingly, it didn't really take as long as you might imagine. I started to notice patterns to the changes I was making and got to what appears to be a well-balanced horn relatively quickly. Again, based on the assumptions that I made. Now, I won't get deep into this, but very quick rundown. I ran frequency simulations looking for geometry that gave me a good resonance at 40 kilohertz along the length of the horn. I kept tweaking the geometry looking for when it wanted to naturally stretch and compress at my specific frequency, instead of, I don't know, when it hit 40 kilohertz wanting to act like an inflatable car salesman. Once happy that I'd found a resonant horn, I ran a harmonic analysis. What that means is I drove the back surface of the horn that I designed with a frequency sweep from 30 kilohertz to 50 kilohertz. To do two things really, to verify the peak at 40 kilohertz and to get some sense of how much magnification I'm getting out of this horn design. So in the chart, starts at 30 kilohertz on the left and sweeps to 50 on the right. You see it comes up at 40 kilohertz. Or, thereabouts. And it's showing about a 9-to-1 magnification when it hits that. So 10 microns in, about 90 microns out. Now maybe not great, I don't know how that stacks up against professional horns, but hopefully that means this thing will do something more useful than just make a fun noise. Alright, so the epoxy's broken loose. I'm not sure if this is a legit way to hold this horn. This is just some packaging, retail packaging. I hope everybody knows what this feels like to cut. If I didn't mention it before, I put in a longer stud, got the whole transducer out of the vise. Don't know if I'm going forward or backwards there, but there you have it. I took out the other X-Acto blade, cleaned out the epoxy, and I sort of pressed in this flat blade so we're pushing right into the transducer. It just kind of crimped in that aluminum. Round two. Nice. Okay, so it looks like this thing starts quacking like a duck, opening and closing. That's probably what killed my epoxy too. I mean, that thing's in there rock solid now, and if I turn it on, it's still in there pretty solid. Let's try it. Yeah, that's doing something. Nice. I want you to see my hand so you get an idea of, the little force that I'm putting on there. I'm really just trying to steer it. Let me get you in closer. There are definitely certain places or certain ways I can sort of steer the plastic so it cuts faster. Let me try some rubber. This is drawer liner for my toolboxes. Oh yeah. It cuts better on the edge closer to the camera. Here's some cardboard. It does the cardboard. I should have gotten thinner cardboard. So there are definitely specific attack angles that this geometry likes. Try some thicker plastic. I've got some plastic tubing and my old hip replacement. These, I believe, are both nylon. Sort of. Not as spectacular as with the cardboard or that thinner stuff. Again, I can feel it kind of going in fits and starts as that, I don't know, blade bottoms out or makes contact somewhere. Deburring tool. Nope. Cardboard. The plastic from before. Let's try this thicker part of the plastic from before. Whew, I'm just an emotional wreck after that. So, the age-old question. Can you make an ultrasonic cutter out of a cheap ultrasonic cleaner? No. No, you can't. Well, I couldn't. Well, sort of. On the one hand, I'm stoked that this horn actually seems to be doing something. Here it is again, off against the same cardboard. Crushy, crushy. So something was happening. On the other hand, it's probably the worst little ultrasonic cutter that couldn't. Again, made a lot of assumptions to get here, and let's not lose sight of the fact that it's only 60 watts. I don't know, likely I'm not at resonance maybe? Perhaps a smidge above or below the peak instead of right on center. At any rate, there you have it. Thanks for watching.